Welcome to this lecture on electric machine design. We will continue our discussion about design of windings. If you remember in the last class, which was the offline class at the university, we talked about the numbering scheme for a typical winding. So in today's lecture, we will take this discussion further and we will discuss some more topics related to design of windings. So we first talk about coil span. So by coil span, we basically mean that the number of teeth embraced by the two coil sides of a coil is the coil span. So the number of teeth of the armature which the two coil covers, so that is the two coil sides cover, is known as the coil span. So in general, the coil span is usually equal to the pole pitch. Usually, the coil span is equal to the pole pitch. Uh, However, some coils are deliberately chorded. If you remember in the offline class, we discussed chorded coils are those coils which do not span the whole pole pitch. They are shorter than the pole pitch. So this is because if you have let's say a number of slots, let's say you have 37 slots and you have 4 poles. So the pole pitch is going to be how much? Pole pitch is going to be 37 by 4, that is 9 and 1/4 slots, right? So this is not an integral number, right? So in this case, you can either have the coil span equal to of either 9 or it could be 10. So generally the rule is to take it to the nearest whole number. So in this case, it's in 9 and 1/4, it's taken to be equal to 9. So in this case, what happens, the coil span is taken to be 9. Okay, so what happens in this case? If the top coil side of the coil lies in slot number 1, the bottom coil is going to lie in the 1 plus 9, that is the 10th coil, right? This is also, if you remember from the class, the first if you remember, in case of the windings that we discussed, the first layer belongs to the is on the top, and in the next slot it goes to the bottom, right? If you remember this correctly, if this is like this, so this goes here and this goes like this. Okay, so the winding starts from the top slot of one coil and goes to the bottom slot of the other slot. So this is about the coil span. These are some basic definitions. You must understand them well and remember them, and these will be very important in the further discussions. Now, types of DC windings. Let's focus and talk about different types of DC windings in DC machines, or the windings in DC machines. These windings are broadly classed into two categories, which is the first category is known as the lap winding, and the other are known as the wave windings. Okay. So the difference between the two windings lies in the following parameters. The difference is in the number of circuits between the positive and negative, between positive and negative brushes, The second difference is in the manner in which the coil ends are connected to the commutator segment. So this is where the difference lies. So the the most commonly used windings are the simplex windings, and we have the simplex lap winding. In the simplex lap winding, we will discuss this in a bit. In the simplex lap winding, the let me write this here. The finish coil of coil number 1 is connected to start S2 coil of start S2 of, we call this finish coil as F1, and the start F2 or S2 of the coil to starting under the same pole as start S1 coil, S1 of coil 1. I'll repeat this. The finish coil F1 of the coil number 1, it is connected to the start S2 of the coil 2, starting under the same pole as the start S1 of coil 1. This will be more clear in the figure that we will see right now. So if you see, if we have the north pole here and the south pole here, notice that I'll be using different colors, so this will help you understand this better. So if this is the south pole, so this goes here, so this goes here, this goes like this. So if this is the commutator segment 1, 2, 3, this is the start S1 of the coil 1, this is coil 1, this is coil number 2, this is side number 1, side number 2, and this is known as side 12 and slide 14. So this is the start S1 point of the coil 1. Then we have the point F1, or what was the name of the point? The finish coil. This is point F1 of the coil 1, and then you have the point S2 or the start 2 of the coil 2, and then you have the finish F2 of the coil F2, and this is connected like this. Okay, so this is what is the simplex lap winding. So in the simplex lap winding, the finish coil F1, that is this point, is connected. So let me highlight this. The finish coil F1 of the coil 1 is connected to the start coil S2 of the coil 2. Okay, the connector connecting the points F1 and S2 is connected to the segment number 2 of the commutator segment, which is adjacent to the start of the segment, commutator segment 1, at which the first coil had started. Is this clear? I hope this is clear. So this is the start 1 coil S1, start of coil 1. Then it goes on to F1 point, and this F1 is connected to S2, which is the start of the coil 2, and these F1 and S2 are connected together here like this, and these are connected to the segment number 2, which is the segment one after the segment at which the first coil starts. So this is about the lap winding. Let me label this here. This is known as the simplex lap winding. Okay, so after this we have the simplex wave winding. Let me write this here. The simplex wave winding. In the simplex wave winding, the finish coil F1 of coil 1 is connected. Let's not call this finish coil. Let's call this finish F1 of coil 1 is connected to start S11 of coil 11. For any particular case which is located under a similar pole to the one under which coil I started. So if you see in the simplex lap winding, what happened? The S2 started at the same pole, like you see here. S2 started at S2 coil goes through the same pole at which the first winding was connected. But in case of the simplex wave winding, it's a bit different. It is at a different location, but it's at under the same polarity. So let me show you this by means of a diagram here. Let me move this to the side so that I can have more space. So if I label this north pole here, then I have the south pole here, and then I again have the north pole like this. Okay, so what is going to happen in this case? If I have the if this is my segment number 1, if this is my coil number 1, this is the finish point, and this is not connected to the commutator segment here, but this goes to the next segment so that it gets connected to the same pole like this. So this is F1, finish F1 of the coil 1. This is S11 or the start of coil number 11. So this is commutator segment 1 to here. This is going to be the segment 12. This is 13, this is 11, and like this there are going to be other segments. Similarly, if you have another coil here, coil number 3, let's suppose, that will go like this. Okay, so then you have this going under the south pole here. Okay, so this is going to be for the coil number 2. Okay, so this is how the simplex lap and the wave windings are different. So in case of the wave winding, the finish coil F1 of the coil is connected to the start S11 of the coil 11, which is located under a similar pole to which the one under which the coil first started. So the wave winding, it starts at the north pole like this, but this point F1 is connected to the pole, is connected to the start S11 of the 11th coil. So let me write here, this is coil number 11, and they are located at a similar pole at which the first winding was connected, the first I mean the winding of the first pole, the pole of the first winding. So this is about the simplex wave winding. Okay, now after we have defined these simplex wave and lap windings, we need to discuss some more detail about the pitches. So we will now talk about winding pitches. So the first pitch, the first subtopic is the what is known as the back pitch. What do you mean by back pitch? The back pitch is the distance between the top and bottom coil sides of a coil. Which is measured around the back of the armature. The distance between the top and bottom sides of the coil measured around the back of the armature is known as the back pitch. So this is a back pitch, and it is denoted by the term YB. YB is the back pitch. Okay, so in the figure, let's try and locate back pitch here. So back pitch is the distance between the top and bottom sides. So if this is the top side and if this is the bottom side, this distance is YB, measured around the armature. So this distance is known as the back pitch, YB. In case of the wave winding, it's the distance this to this, again this is YB, the distance between this point and this point is YB. This is the back pitch. Now since this YB is measured as difference of an even and an odd number, okay, this back pitch is always an odd number. Okay, this is just some general information which you must keep in mind. The back pitch is always an odd number. Okay, in case of this lap winding, if you see that the sides of the coil, the sides of the coil 1 are 1 and 12. Okay, so 1 is an odd number, 12 is an even number. The difference between the two is, let me write this here, yb for this winding is equal to 12 minus 1, which is equal to 11. So this is an odd number. Okay, similarly in case of this winding, I forgot to write the sides here. This is 12, this is 14, this is 23, and likewise. So in this case, the back pitch is again 12 minus 1 is equal to 11. This is the back pitch in the two cases. Okay. So what does this back pitch help us identify? This back pitch of a coil, it determines the size of the coil, and it is nearly equal to the coil sides per pole. So the back pitch, it helps in determining the size of the coil and is nearly equal to the coil sides per pole of the winding. Okay, so this is about the back pitch. The next is the front pitch. The front pitch, it is the distance between two coil sides connected to the same commutator segment. The distance between the two coil sides connected to the same commutator segments is known as the front pitch, and it is denoted by YF, the front pitch. Okay. So the front pitch in case of the lap winding here on the left hand side is the difference between the, let me go back to the definition. It is the distance between two coil sides connected to the same commutator segment. So if you take a look at this winding and see that this winding, this coil side and this coil side, they are connected to the same commutator segment number 2. So the distance between these two is known as the front pitch. It is denoted by YF. This is the front pitch. Similarly, if you see for the segment 12, you have the side 14 and 23, sorry, not 14 and 23, but 23 and 12. Let me just, the 23 and 12 connected together. So this and this, they are connected together. So this is again going to be the front pitch for this wave winding. Okay. So this was about the front pitch. Okay, so for the lap winding, let me go back to the lap winding. So for the lap winding, what is the front pitch? it is 12 minus it's 12 minus the 3 23 minus 12. So you can find out the I mean the back pitch from the coil sides, the number of the I mean the serial number of the coil sides, and then you can subtract the two and you can get this front pitch. Okay, so this is about the front pitch. So in this front pitch, it helps in determining the type of winding, but does not affect the size of the coils. Okay, so if you are given, let's say if you are given a certain winding arrangement, I think you will be able to with ease you will be able to calculate the front pitch if you are given the I mean the nature of the coil, nature of the winding, and you are asked to calculate the front pitch and the back pitch. I think you can easily find it out. So okay, so this is about it for the front and back pitch. Then you have the third type of pitch which is of interest to us. It is the winding pitch. The winding pitch, it is the distance between the starts of two consecutive coils measured in terms of coil sides. Okay, so distance between the starts of two consecutive coils measured in terms of coil sides is known as the winding pitch, and it is designated by a capital Y. Okay, so this capital Y is equal to YB minus YF for a lap winding, and it is equal to for the wave winding. Okay, so this is about this is the a relation between the various pitches with the winding pitch Y. Okay, so if you see in the first case, in the lap winding case, this is YB, this distance. So if you subtract this distance from it, what distance remains? It is this distance. So this distance is known as the winding pitch Y. Okay, so let me just erase these two, and then we can say that this is the winding pitch. On the other hand, if you see in case of the wave winding, it is this distance plus this distance, because we said that it's the it's the distance between the starts of two consecutive coils measured in terms of coil sides. So if we say that this coil side starts at 1, the next coil side starts at 12, so this distance the distance between these two adjacent coils is given by this. So if you see this this is YB and this is YF, so if you add the two up together, you will get the winding pitch y, which is the distance from this point up to this point. Okay, so the winding pitch here is 12 minus 2, sorry, 11 minus 2, and it's 11 minus 9 rather, 11 minus 9, and it's equal to 2, and in this case it's 11 plus 11, so it's 22 in this case. So this is about a winding pitch. The next is the commutator pitch. It is the distance between two commutator segments to which two ends start and finish of a coil are connected. This is measured in terms of commutator segments, and it's denoted by YC, commutator pitch. So if you see YC in the lap winding, we had this this was this coil number 2, and this was coil number 1, so the difference between the two is 1. So it's case of in case of the lap winding, it's the difference 2 minus 1, so it's 1. In case of the lap winding, YC is equal to 1 for the lap winding, and in case of the wave winding, it is this 12 minus this 1, so YC is equal to 12 minus 1, which is equal to 11 in case of the simplex wave winding. Okay, so this is about the commutator pitch. So commutator pitch is the distance between the two commutator segments to which the two ends of the coil are connected. So if you analyze this winding arrangement in totality, and if you trace it all over the place, so in case of the simplex wave winding, commutator segment adjacent to the first one is reached after traversing through one coil. Adjacent segment is reached after traversing through one coil. Okay, and in case of this is for the simplex lap winding. For the simplex wave winding, the adjacent segment is reached after traversing through P by 2 coils, where P is the number of poles. So after P by 2 coils, the next commutator segment is reached. Okay, so this was all about today's lecture. I'll just briefly take a quick overview of what we discussed today. We discussed coil spans. We discussed the major two types of windings, the lap and the wave windings. Then we drew the fingers. Then we discussed some various pitches. We discussed the back pitch, the front pitch, the winding pitch, and the commutator pitch. So this was all about today's lecture. In the next lecture, we will further talk about this winding arrangement and continue this discussion, and hopefully try to finish up this unit as soon as possible. So I'll see you in the next video.